Okay, I just want to go through the calculation for Laboratory 2 so that you know how to complete the submission. So, I'll have a look down through this. The experiment itself involves working out which of 3 brands of bleach is the best value for money in terms of its active ingredient. The active ingredient is sodium hypochlorite. Now, it's very often the case that in commercial products they don't use moles per litre when writing the active ingredients on bottles or containers. They're much more likely to use weight, that's mass, percent, which means in 100 millilitres. So it's weight in 100 millilitres, weight to volume, percentage. And that produces a more human figure that people can grasp, rather than the very small numbers that very often we're dealing with when we're using moles per litre, which of course is the correct unit. But people can't get the hang around what a mole per litre is, can't get the hang of it. So the manufacturers use weight percent. Now, the active ingredient in bleach is OCl-, and what happens is that when you add it in an acid solution to water which contains chloride, it produces chlorine, which is what bleaches things. This is the active ingredient, the chlorine that's released. Now, very often it's confusing. Where's that chloride coming from? It's coming from the water. Bleach is always in a dilute solution. It will always grab spare chloride from the water to produce its chlorine. So although it's not strictly, it's not obvious where that chloride's coming from, it's coming from just from water contained in the water that it's been put into. So what we're going to do is work out the concentration of the sodium hypochlorite 3 ways. We're going to do it as moles per litre, and then we're going to convert that into a weight percent of the active ingredient, sodium hypochlorite, and we're going to work it out as available chlorine, which are the two measures which are put onto the bottle. I'll come back to that in a minute. What we'll first want to do though is look at the reaction that we're going to be doing. We've got hypochlorite, the bleach, and we measure out 3 mils of it, and we add excess acid, glacial acetic acid, and we add excess sodium iodide. And what happens is that instantaneously the hypochlorite turns into chloride, so it goes into a colourless chloride ion. The previously colourless iodide ion is released into the solution as iodine, which is bright purple. So our solution has instantaneously gone purple. The acid is in there because it's required to balance the chemical equation. We require the reaction eats up acid. So that's the reaction that's occurring when you prepare your solutions. And then what we're going to do, you see how the hypochlorite forms iodine in a ratio 1 to 1. So for every mole of iodine that's formed, it came from 1 mole of hypochlorite in the bleach. If we then remove the colour by quantitatively titrating with sodium thiosulfate, we can work out how many moles of iodine were there, and from that work out how many moles of hypochlorite were in the original solution. Do notice that the reaction between iodine and hypochlorite is in a ratio of 2 to 1. The amount of thiosulfate that's reacting with the iodine is twice the amount of iodine that's present. Okay, let's go through the calculation and take you through it. Now, I don't know which bleaches we're going to be using this year, so you're going to need to put the bleach brand in, and nor do I know the concentration that the technicians will prepare, but they'll prepare a solution and then you will be given the concentration of the thiosulfate solution, and you'll do a series of titrations. So let's pretend for the sake of argument, that we got a titration that was 17.0 thiosulfate to make it go clear, 17.1, 16.9. We've got very good concurrent results. And one thing that you should be able to see from the experiment we're doing is that even though individuals, groups, may produce answers which are a bit wayward or are not exactly the same, once they're collected together and averaged, then you should get a result which is consistent with the real concentration of hypochlorite in the bottle. And it's one of the things of chemical analysis that you can't rely on just one experiment done by one experimenter. It's much better, you'll get much better answers if you have multiple measurements by the one experimenter, and then a series of independent measurements are made by different people in order to get over any experimental systematic faults that the individual is making. And by doing that, you get answers which are very close to the real thing. So let's suppose out of our thiosulfate solution, 1.1030 molar, the average amount we had to add to clear the solution was 17 mils. It should be to just 3 significant figures, but it's producing it to 4. Okay. Then we need to look at the equation, and the reaction that we're doing is that the thiosulfate, the hypochlorite, is reacting with acid to form 2 iodides. We need to balance this chemical equation, so we need to balance the waters on that. We've got 3 hydrogens on that side, we've got 2 on that side, so we're going to need at least 3 on that side and 2 on that side. And take that out, that should be sodium. See if that's balanced. Yep, that's now balanced off. Okay, we've got 2 moles of acid balanced with the 2 moles of iodide. So that's the balanced chemical equation that we're going to be doing. And you see 1 mole of hypochlorite produces 1 mole of iodine. Then what we're doing, we're titrating the iodine with the thiosulfate, I'm afraid I can't put the superscripts in still into the computer program. It's the bane of computer programs writing chemical formulae. Produces iodide, and tetrathionate, which is S4O6 and then 2 minus. Okay, so obviously this is going to need 2 moles to balance it. So from that, the ratios are that 1 mole of hypochlorite produces 1 mole of iodine, and that reacts with 2 moles of thiosulfate. Alright, so how much thiosulfate have we added? Well, clearly it's the average of our titrations was 17, and it's 17 over 1,000 because it has to be converted into litres, times the concentration, which is 0.1030. Pulling up the calculator, 0.1030 times 17 divided by 1,000. 0.001751. 0.001751. That's how many moles of hypochlorite, 0.001751. The moles of hypochlorite that's equivalent to is half that number. Look, it's 2 moles of thiosulfate for every 1 mole of hypochlorite. So it's that divided by 2. 0.0008755. moles of hypochlorite. The concentration of hypochlorite in the 3 mils, which is what you transferred in, is equal to the number of moles divided by the volume. So it's 0.000875 divided by 3 divided by 1,000. That's 3 in litres. So I've converted it to litres by dividing by 1,000. So let's do that calculation. Number of moles divided by 3 times 1,000. 0.2918 molar. 0.2918 moles per litre. That means the concentration of that is whatever you put, and you put 0.2918. Now we're going to convert that into a weight percentage. Okay, now let's go back to the original part of the early pages to convert our moles per litre into weight percent of dissolved sodium hypochlorite. What we do is we take the concentration 0.2918 and we multiply it by the molar mass, because this is a number of moles, molar mass of sodium hypochlorite, which is 74.5. And then, well, I'll do that first. So this is the number of moles times 74.5. That's 21, and that's per litre. This contains 21.74 grams of hypochlorite per litre. So per cent, or per 100 mils, we need to divide by 10. 2.174. So let's go down. .174. Right, let's go back up to the available chlorine and we'll do the same calculation. 0.2918 is the concentration. In terms of available chlorine, the number of moles of hypochlorite equals the number of chlorine. Look at the equation at the top here. The number of moles of hypochlorite is equal to the number of moles of chlorine. The extra chloride comes out the water. Okay, so it's written here, dissolved hypochlorite is equal to hypochlorite is equal to the available chlorine. So we've got a concentration of 0.2918, and instead of multiplying by the molar mass of hypochlorite, we'll multiply by the molar mass of chlorine, which is 70.9. And again, this is 20.69 grams per litre of available chlorine. So divided by 10 into percent. 0.2069. Oh, sorry, I've just 2.069. Weight percent chlorine. So it's a reasonably simple calculation. Now, up the front, or your supervisor will give you the volume of the bottle of hypochlorite, or the bottle of bleach that we're looking at, and let's say it came out of a 1 litre bottle, and that it cost $2.50. Oops, 250 cents. Now the total available chlorine in the bottle is 2.069, which is what's available in 100 mils, and we've got 1,000, so it's going to be 20.69. Simply multiply the amount of chlorine in the bottle, in weight percent, divide that into the volume of the bottle, and then use that as a factor to multiply. So here I've got 1 litre of hypochlorite, and this is percent, so there's 10 100-gram aliquots in a litre, so I'll multiply it by 10. And then simply to work out the cost of the ingredient, the active ingredient, you take the cost in cents, and you divide it by the number of grams of available chlorine. So what does that equal? 250 divided by 20.69. It's, well, that seems very expensive. Hang on a second. Doesn't seem right. 250 cents, and it's 20.69, so I'll just check that again. 20.69 divided by 250 divided by, I have to clear it, sorry. 250 divided by 20.69. Yep, that's 12 cents per gram. So that's a very expensive bottle that I've just invented. You'll do that on your actual cents per gram. Okay, so you simply divide the cost by how many grams there are in the bottle, and then what you'll do is you'll collate the results for the class, and you work out which brand of all the ones that's measured it represents the best value for money, and that's how you'll do the calculation for presentation in this experiment.